Okay, so here's a topic that everybody can agree is relevant. If you're not a vegetarian, then you might enjoy something like this. If you are vegetarian, then perhaps you can imagine this being replaced with a soy burger. What we're going to be interested in here is simulating the heating up of food by a combination of radiation and convection. And we can see in this case, we've got a piece of meat on the grill. We've got radiation coming from these coals. We also have hot air rising up from the coals and transferring the heat by convection. On the top of the meat, we have heat being radiated out from the hot surface here, and we also have convection air flowing across the surface and removing heat that way. So we want to include those in the model, and before we set it up, we should take a look at some of the criteria. We'll simulate a T-bone steak, and here's a picture of the T-bone. We are clearly going to need to include radiation in the model. Here's an infrared photograph, and you can see the the hot warm colors here from the infrared radiation. And the cold colors here are where the food is blocking the infrared and absorbing it, so that energy is being transferred to the food. And the temperature that the piece of meat is achieving is really going to determine what the how well it's cooked. And so here are the different grades, extra rare or rare, all the way up to well done. And here's the description, but we can quantify these with the temperature at the center of the piece of meat, ranging from the mid 40s degrees C up to 70 to 100 degrees C for the well done. We can also see if the center gets above 100 degrees C, then it's blackened throughout. And in order to get above 100 degrees C, what that means is that essentially all the water has been boiled off, because material will only reach 100 degrees C. It'll reach 100 degrees C that if there's water present, the water will boil, and then any additional heat that's put into the system will vaporize water, and so that heat will be consumed by the latent heat of vaporization, and that will go on until the water is gone, and then you can heat it up above 100 degrees C. So we have these criteria that give us how well done it is based on the internal temperature, but we also recognize that if we're heating it like this, that the outside temperature could be a good deal greater than this. And so one thing that we'll want to consider is with these internal temperatures, what is a corresponding outside temperature. It might be greater than 100 degrees C, in which case maybe the outside is getting a little bit crisp. Although what I should point out is that in this particular model, we're not going to consider the boiling of water. And so that sink of heat from the latent heat won't be considered. So we may have temperatures that are above 100 degrees C. One of the other criteria that we need to consider is the temperature with respect to the microbial population. One of the things that we want to do to cook food to make it safe to eat is kill the microbes, and it takes anywhere between 60 and 70 degrees C to kill microbes. I've looked at several sources and it ranges somewhat, but we'll want to have temperatures in that range or greater to make sure the microbes are killed off. So the conceptual model that we'll use will consider grilling, and so we'll have a heat source here and radiation and convection transporting the heat up to the bottom of the material, and then we'll also have radiation and convection transporting heat away from the top, so long as this temperature is greater than the ambient. So we warm up this side, and then we would flip it over and we would reverse these boundary conditions. So we're going to need boundary conditions that flip over with time. That's how we'll have the flipping of the stake represented. So here's the model, and this is our T-bone. Looks about the right shape and thickness. And so the way I set this up was to create a shape here that was about right, and then I extruded it to get this this particular shape. And this required doing something a little bit different than what we've done before. So here is the geometry that I drew in the work plane, and you know, this is fairly tricky to draw within COMSOL. It would be nice to just be able to click out a few points, but it's not really quite clear how to do that. So what I did instead was to draw this out in a drawing package that is able to make a .dxf file format. I used a package called AutoCAD, and the university has a site license for AutoCAD, so you can get it on your computer, and it should be available on the computer lab. This gives you a great deal of flexibility. You can draw very complicated objects, much more complicated than my beautiful T-bone outline here. But nevertheless, what I wanted to do was show you that this is really an avenue that's open to you for bringing in geometries into COMSOL to analyze. And so what's done is to go to import, and I found the file that I made. This is a file with a .dxf file extension, and I'll give you this file so you can use it for your model. And then imported it, and when I imported it, let's see if I can build that. So there's what it looked like at first, and this is the scale. So when I drew this, there's a little bit of a disconnect between the scale that it was drawn in AutoCAD and the scale that it is in COMSOL. And so right now we've got a T-bone that's probably the biggest T-bone in the world. It's a 3.5 meter long T-bone. So that's probably not what we want to deal with. So I used the scale function to reduce the size, and just multiplied the whole thing by this factor here. And when I did that, I have a reduction in size down to now 0.2 of a meter. So that seems more reasonable. And the other thing that I wanted to do was to round off these corners. And that's possible to do in AutoCAD, but I just brought in this very simple diagram. And so I used this command here. A fillet is where you round off the edge of usually it's of a machined part, but in this case it'll be our T-bone. So I applied this to the drawing. I had selected each one of those corners, and we get this this effect. You can change it around a little bit. If you have a larger radius of curvature, then you can get well, I guess it didn't like that particular value. Let me try making it a bit smaller. So there's a smaller radius of curvature, and you can see that it's tighter. I would like to try making it a little bit bigger. Okay, there you go. So there's a bit bigger. I guess what happened if it was 0.04, maybe these arcs are starting to interfere, and it didn't like that. So I played around with this, and 0.01 looked about right. So I could believe that was a T-bone, and then I just simply extruded it and made this geometry. And 0.02 is 2 centimeters thick for the stake. You know, that seems like a reasonable size. Okay, so we're going to have water as a material, and under the variables, well, actually, let's take a look at the physics first, and then we'll get to the variables. So I used heat transfer in solids, and I want heat transfer in biological tissue. Seems appropriate. And this was all this stuff was just defaults. And let's see, this is also where we can supply the properties. So there's that thermal conductivity that we saw earlier. The density of meat, it's right around the density of water, so I made it a little bit greater. And the heat capacity, remember water was around 4,000, so this is a bit lower than water, but I was able to look up and find this value. And so that's the properties for our meat. And so what I did to set up the initial conditions, we're just starting it off at ambient temperature, so we're going to have to heat it up when we put it on the grill. So to do the cooking, we're going to have convection and radiation. Those are the two mechanisms that we saw in the conceptual model. So I've got two surfaces. The surface one, let's take a look like this. So this is the upper surface that's selected now, and that's surface 1, and it's surface 4. So for surface 1, I have convective cooling, and I'm going to give it a temperature and a heat transfer coefficient. Those were the two specs. And under ambient to surface radiation, then we need to give it the emissivity. That's going to be a parameter that describes how readily it absorbs and emits radiation, and also then the temperature. So in both cases, we have to give it a temperature, and this is the temperature of the ambient conditions, so kind of your far field temperature. So in one case, it will be the ambient temperature out on the grill, and in the other case, when it's face down, it'll be the temperature of the coals. Okay, so I did that for one side, and then for the other side, I just have the same settings, but I'm giving it temp side 2 in both cases. All right, so that's how I set up these boundary conditions. And then we're going to want to cook this for a while and then flip it. So the way I did that was with the boundary conditions, the temp side 1 and temp side 2. So I'm going to make temp side 1 equal to, well, let's see, I forget how I did it. We can diagnose though. Here's temp side 1 and temp side 2. So temp side 1 is going to equal cook side 1 times the cooking temperature plus the ambient temperature times 1 minus cook side 1. Okay, so cook side 1 is a step function, and we'll take a look at the step function. It goes from 1 to 0, and it does a transition at the time called turn t. So this is the time when you turn it over, and we transition it over 3 minutes, but I think that would probably be really more realistic if it was more like 0.2. So we have a much more rapid turnover when we're flipping this steak over. Okay, so that's step 1, and let's go back to the variables. So step 1 goes from 1 to 0 at the turn time. So initially, at early times, cook side 1 is equal to 1, and so the cooking temperature equals cook temp plus, since cook side 1 equals 1, this is equal to 0. So initially, cook side 1, the temp side 1 equals the cooking temperature, and temp side 2 equals, what I did was just reverse this cook side 1 and the 1 minus cook side 1. So instead of that, I have that, and then down here I have 1 minus cook side 1 and replaced it with cook side 1. Okay, so from time equals 0 to turn t, temp side 1 is equal to cook temp, and temp side 2 is equal to ambient temp. And then here's where I set up those temperatures. And I looked at the temperatures of grills, and these temperatures need to be an absolute temperature, degrees Kelvin. So I took the temperature of the grill of 250 degrees C and turned it into Kelvin. And then the convective heat transfer coefficient, I found several values for this. I found a paper that looked at heating in an oven, and in an oven the convective heat transfer was about 65 in these units. But I thought that in this case, because it's outside and there might be wind blowing, and so I used a lower value. But I found another reference that said that in general the convective heat transfer coefficient for horizontal planes was between 5 and 25. So this is roughly midway between that. But it could be that this is underestimating. Emissivity, so emissivity ranges from 0 to 1, and a perfect black body is 1. So this seems like a reasonable value. So those are the parameters. And I guess the only other thing is the turn time there. So we're flipping the steak at 5 minutes. And then I guess the other thing is, what we might do is also have another parameter that's the total cook time. And so we set this up. Yeah, so what I'm doing is cooking it for a total time of 12 minutes and flipping it at 5 for this particular simulation. And so I think this setup is nothing really too unusual. I'm plotting it while I'm solving it, and we just have this one set of physics, so we can just go ahead and solve this. And the solution goes really pretty quickly. We can see our steak, I guess it's upside down, it's grilling the top first. Now we grill the bottom, and there's the result. So here are the thermal profiles. So the first set of profiles is done here, and let's be sure about that. Let's read. So we flip it at 5 minutes. So there's the first set of profiles. Okay, so this side is getting heated first, and by the time we flip it, well, it's not quite. This is a little bit after it's flipped. We can see the effect of starting to heat on this side. So what I guess we can see is that for this amount of heating at this temperature, we heat the outside up to 90 degrees, and we barely even heat the other side, the opposite side, at all. So, a lot of times when you're grilling a steak, before you flip it that first time, the top of the steak doesn't really look like it's changed much. And this is showing why that is. It hasn't really penetrated all the way. We've gotten the outside up high enough to kill off any microbes on the outside, but certainly not yet on the inside. So we flip it over. And when we flip it over, now we're going to cook the other side for 7 minutes in this scheme. And here's what we get. The temperatures now go up here above 100, and we can see that this is right here. I guess we have a little chunk in here that's below 60 degrees. And so if we were trying to get things above between 60 and 70, we still have the interior that hasn't quite done that. So if microbes were able to penetrate to the center, then we wouldn't be killing them. But I think most of the time we're interested in the external surfaces, and so we certainly raise those temperatures well enough. So let's see, the internal temperature is 60, just about 60 degrees, and so that would correspond to medium rare. Medium rare cut, so well, it is that's what you get from that scheme of temperature increases, or that from that. So just one final comment. In this simulation, we've got this zone right here where we're predicting that the temperature is above 120. Now, if we adjusted this model so that we included the boiling of water, then what we would do is have water stored in the meat, and when it reached 100 degrees, so right between the black and the blue time periods, once we got into this time period, what we would be doing is having the heat transfer across the boundary, and then that heat would be then absorbed by basically consumed by the latent heat. That would cause water to go to steam, and it would hold the temperature at 100 degrees. So the temperature profile would really, instead of being up like this, it would really come across like that until all the water was boiled off, and then it would start to rise. Okay, so because we've left that out, this part of it is really not going to be quite accurate. But nevertheless, I think we can use this as a good assessment of what would happen without having that particular specific process included. That's something that we would include later.